All right, it's 9:05, so let's go ahead and get things started. Thank you all so much for coming to the 2024 Wormit Award webinar. This webinar is going to be presented by the award winner, Adam, who is here with us. We're very excited to have him, and he's going to be talking about some of his work with GTO-based periodic methods in Q-Chem. And Adam got his BA at Cornell in 2018, and then he moved on to Martin Head Gordon's group at UC Berkeley, where he did his PhD work, which he wrapped up in 2023, and he's currently working in Junho Lee's group over at Harvard, doing some really exciting work with electron-photon coupling, and also working on implementing QCPBC, which is our new code for handling periodic systems in Q-Chem. And he's done a lot of really amazing work, both within Q-Chem and also from a scientific standpoint as well. And so we're just really excited to have him here and to have him be the recipient of this award. I'm going to go ahead and hand this over to Shirin, one of our board members, who's going to give a couple of opening remarks about the webinar, or not about the webinar, but about the award. So, yes.
You see my screen?
Yes, we can see your screen.
Very good. Welcome everyone to the 9th Developer of the Year Michael Wormit Award. My name is Shirin Faraji, and I'm a professor of theoretical and computational chemistry at University of Düsseldorf, Germany, and I will be chairing this award ceremony. About 9 years ago, on March 15 of 2015, the life of Dr. Michael Wormit was cut short. It was and still is a tragic loss for all of us. Michael was a husband, a son, a friend, a great colleague, and a great mentor. We shared an office together, by the way. He was also a part of a Q-Chem developers community. We gathered here today to remember Michael and to celebrate his accomplishment and his contribution to our community. His life was short, but he left a mark, and his work will continue to make an impact. And this is something we should cherish and remember. To always remember Michael's contribution to Q-Chem community, Q-Chem Board of Directors established an award in his name. And on behalf of the Board of Directors, let me introduce Michael Wormit Award. The award has been established in August 2015 to recognize excellence in developing new methods and algorithms in the area of the electronic structure and implementing these methods in the state-of-the-art computer code within Q-Chem Open Teamware Community Project. This award is given annually and includes a certificate, which I will present today, and a $500 prize, which I'm not going to present today. By this award, Michael is remembered for developing a state-of-the-art algorithms and computer codes for many body methods and for his leadership in the community building, educating and mentoring junior team members, and software infrastructure development. Any member of the Q-Chem developer community is eligible for the award. The selection criteria are scientific innovation, excellence in code development, contribution to infrastructure, and developers community. Nomination is sent annually by January 15 to Q-Chem office. This award was given in San Diego in March 2016 to Evgeny Epinovsky. So I can come to the list. You can see the former winners. In 2017 to Andrew Gilbert, in 2018 to Alec White, 2019 Junho Lee, and together to Pavel Pochilko and Yuji Mao in 2020, and Marta Lopez Vidal in 2021, Cynthia Feng in 2022, and Adrian Demvolf in 2023. And today, the 9th edition of the Michael Wormit Developer of the Year Award goes to Dr. Adam Rettig. And please join me virtually thanking Adam for his contribution to Q-Chem community and congratulate him on being selected as the recipients of the 2024 Developer of the Year Award. I wanted to introduce Adam, but Shannon did the job. But I just add that the nomination of Adam was mainly based on his work, on his PhD work on the development of QCPBC package that he has started there, and he's still continuing doing an excellent job in this direction, which we are very fascinated. Using atom-centered Gaussian type orbitals that enables to study periodic systems, which is also the title of today's webinar, developing GTO-based methods for modeling periodic systems in Q-Chem. And with that, I would like to also show the certificate signed by our president. And you will receive a framed version of this certificate by post, that you can put it hopefully somewhere nice to always remember this accomplishment. And the floor is yours, and we are very looking forward to hear about your exciting development and results about QCPBC.
Thank you for that very nice intro. A very generous award. Okay. Okay, I'm sharing my screen. You can see it? Okay, awesome. Yes, hello everyone. So I'm Adam. I'm a postdoc at Harvard currently. And so I wanted to use this talk to sort of advertise our periodic boundary conditions code that we've been adding to Q-Chem over the last year or two. So this talk is going to be geared sort of towards what I imagine the typical Q-Chem developer is, I guess, which is more of a molecular quantum chemist in framing framing periodic systems in sort of a molecular context. Solids are quite a bit different than molecules. And Q-Chem is first and foremost, of course, a molecular quantum chemistry package. So for molecules, you just have a handful of nuclei surrounded by a whole bunch of vacuum. So to run an ab initio calculation, you just specify your nuclei and your number of electrons. Solids, on the other hand, you have to specify your nuclei, your electrons, and as well as a set of lattice vectors, which define your unit cell. So I'm showing kind of a 2D picture here of a diamond. So using these lattice vectors, you can repeat your unit cell infinitely in every direction. So this gives you the sort of infinite periodic lattice that makes up your solid. So this is, of course, quite a bit different than the case of molecules. You have an infinite number of atoms, an infinite number of electrons. So in order to actually simulate this system, you need to take into account the translational symmetry that a solid obviously has. So since any one of these unit cells should be no different than the other, we know that our density has to be exactly periodic along our lattice. So the density at a point in one unit cell should be exactly the same as the density in a different unit cell at the corresponding point. So Bloch's theorem tells us that the molecular orbitals that we're using to make up these electron densities in our SCF calculation should be periodic then up to some phase factor, which will get canceled out in the density. So you can write it as some e to the I kr here. So another way of framing Bloch's theorem here is that our orbitals can be written as a cell periodic part, this U here, which is exactly periodic along our lattice, much like the density, times some plane wave, e to the I kr, with some momentum k, which is known as the crystalline momentum or the k point. So Bloch's theorem gives us sort of another way of looking at solids where rather than trying to model every single atom in all of our different unit cells, we can model just one unit cell, but consider every possible value of k or k point. Of course, there's also an infinite number of k points, so that doesn't seem to help us so much at first. There's a couple things that make this tractable. The first is that the only unique K points are contained within one unit cell in reciprocal space. So we call this space the first Brillouin zone. So we only have to consider K points that are within this unit cell in reciprocal space. The other thing that helps us is that the cell periodic part of our orbitals is expected to vary pretty slowly in K space. So we can actually integrate K space numerically. So we do this by generating just a uniform mesh, a uniform grid in K space, which we call a Monkhorst pack mesh. And then you sort of perform an SCF calculation at each of these points in K space to get to your overall energy. So if you want to get a very accurate result, you're going to have to use a very fine mesh and a lot of K points. If you want a less accurate result, but more quick, you can use a more coarse grid. So this is another knob you can tune when running your SCF. So the way this looks for your results, whereas for a molecular SCF, you get out a discrete set of orbital energies at the end. For a periodic SCF calculation, you end up with a discrete set of orbitals for every single K point. So if you plot these discrete set of orbital energies over some path in K space, you end up with these nice band structures that make up our solids. So you can tell right off the bat that we have to sort of perform a separate SCF for every single K point. So there's obviously going to be an increase in computational cost for periodic systems as opposed to molecular systems. So for pure DFT, for example, you end up with an extra factor of NK, your number of K points, just based off of having to diagonalize NK different Fock matrices. So to run our SCF calculation, we have to use a basis set which enforces our periodic boundary conditions as well as Bloch's theorem. So there's two main choices of basis sets which are used commonly today. The first is probably a bit more common, is plane waves. So these are convenient because they're inherently periodic, since they're plane waves, and it's very easy to compute matrix elements between your different basis functions. And there's also just a single parameter to define your whole basis set. So you just provide the maximum momentum you want to consider in your basis set, and you generate all plane waves up to that momentum. So it's very easy to define your basis set. The downside of plane waves is that they're not very compact. So electrons are not often plane wave shaped, so you need a whole bunch of plane waves to represent your electron density in some system. So you can easily get into the millions of plane waves, which is a very, very large basis coming from molecular quantum chemistry. And the other part is that the number of plane waves you need to represent core orbitals is just totally impossible to use, practically speaking. So you cannot model core orbitals using plane wave basis sets. So plane wave based codes typically rely on pseudopotentials, or they have several other tricks if they want to explicitly model core electrons. The other choice of basis set you have, which has been kind of growing in popularity recently, although it's been around for a long time, would be crystalline Gaussian type orbitals. So this is kind of an extension of the GTOs that we know and love from molecular quantum chemistry. So the GTOs are not, of course, periodic inherently, so we have to make them periodic by performing these lattice sums. So you just stick a GTO in every unit cell in your lattice, and then you tack on an extra phase factor, which gives you the K point dependence. So these are nice because they are very compact compared to plane waves. So you use maybe 20 or 40 basis functions per atom in your unit cell. And it's very easy to model core electrons. You just use very compact Gaussians. The downside is that they can be pretty expensive to evaluate matrix elements for. So while we have analytical expressions for Gaussian type orbital integrals, when we add this lattice sum into our basis function, every single matrix element becomes an evaluation of many, many different molecular GTO integrals. So this can add up very quickly, and matrix elements can be expensive. The other downside is that you have a different basis set for every single atom. And convergence to the basis set limit is not quite as straightforward as plane waves. You kind of rely on people developing these GTO basis sets that have nice convergent issues and eliminate linear dependencies as well. So that can also be a downside. Q-Chem is, of course, built upon GTOs, so that's also what we're going to be using for QCPBC. Although we will also be using a little bit of plane waves through the Gaussian plane wave technique. So this is a method for handling the 2-electron integrals. When using GTOs, it turns out that the lattice sums that are included in your 2-electron integrals do not converge because the number of molecular integrals included grows more rapidly than the 1/r decay of your electron repulsion integrals. So you have to use some sort of trick to handle the J and K terms when doing GTO-based periodic boundary conditions. So there's a bunch of different techniques people use these days. The one we're using is known as Gaussian plane wave, or GPW. So this is really just a density fitting technique with a very specific choice of auxiliary basis set, namely plane waves. So like within any density fitting approach, you can represent products of orbitals as a linear combination of auxiliary basis functions, which in this case is just plane waves. So you can write your products of orbitals as linear combinations of plane waves with some fitting coefficients C. And since we're using plane waves, these fitting coefficients are easy to obtain just using a Fourier transform. So we use the fast Fourier transform, which are very optimized these days and very easy to use, to evaluate our fitting coefficients. You can then plug in this expression for mu nu and also lambda sigma to get your 2-electron integrals as just contractions of your C matrices or FFT coefficients, along with your Coulomb kernel in reciprocal space, which is just 4 pi over g squared. So this, by using plane waves, we are kind of inheriting some of the benefits and also some of the detriments of plane wave-based PBC calculations. So namely, this can be pretty fast since FFTs are pretty quick. So evaluating this can be pretty quick. However, by performing these FFTs, we have to store our basis functions on a grid in real space. And depending on the fineness of the grid, this can be very memory intensive, as I'll point out a bit later. And also the number of plane waves we would have to use to model core electrons, again, would be too high. So by using Gaussian plane wave, we are limiting ourselves to pseudopotential calculations as well. So this can be very quick, but memory intensive and no core electrons. This is the moral of the story. So the typical structure of a Q-Chem calculation, at least from maybe a data flow sort of standpoint, might look like this. So maybe I'm running a calculation which looks like, it looks like I got a question here. Are periodic CGTOs based runs devised to run on GPU? Our code is not. I have not done any GPU developments, at least for this. I think there definitely are some codes that do utilize GPUs as well, but not Q-Chem currently.
Yeah, sorry, I didn't mean to cut you off. Go ahead and.
Sure.
So I should have mentioned this at the beginning, probably. Usually you are free to post your questions in the Q&A section, but we usually try to answer the Q&A at the end. We just like leave a little time for that.
Okay.
So yeah.
Sorry, I won't read the questions then.
Sorry
until
about
then.
Thank you.
No worries. Okay, so a typical Q-Chem calculation might look something like this, where maybe I'm running an SCF at the start, which runs through the libgscf library. It's using libham to represent our Hamiltonian, which will hold all of our different contributions to the Hamiltonian, like the kinetic and the Coulomb, maybe the exchange if you are using a hybrid functional. And to actually compute these flock matrices, you're eventually calling libqints, or maybe libint, to get the actual molecular integrals. Maybe after the SCF, I'm running a geometry optimization job through libopt3, which is gonna use the gradient builder in libham, which eventually uses derivative integrals from libqints as well. Then maybe after my geometry optimization, I'm calling a couple cluster job running through ccman2, which performs contractions using libtensor, which is eventually populated by, again, libqints. So the QCPBC structure is going to look very similar to this, with kind of one important caveat that we've added this new library, libPBC. So this kind of adds all the routines we need for PBC calculations. So it's going to extend a lot of these libraries, like libgscf. We're adding some problem classes to perform SCF calculations that are k-point aware, as well as different libham contributions. However, it's also going to function as a bit of a wrapper on top of libqints. So if you think about a typical SCF, when we are building our flock matrix, for the 1 electron terms, we want to perform these lattice sums. So we need to make a bunch of libqints calls by summing over all of our different cells. So the libPBC will take care of this. It's going to call a libqints to get, say, your kinetic integrals. It then shifts your basis to a different unit cell, calls libqints again to get the next batch of molecular integrals, and it sums them all up with the appropriate phase factors to get your periodic integrals. For the 2 electron integrals, we said we need to use this Gaussian plane wave technique. So libPBC also does that. It's going to evaluate your basis functions on a grid. It's also going to perform the FFTs, evaluates your kernels in reciprocal space and FFT back. So libPBC will take care of all of this. So you can kind of think of it as a wrapper on top of libqints, where it'll either evaluate your GPW-based integrals or make a bunch of libqints calls and perform lattice sums. So I'll say that currently we've added libopt3, libgmbpt, and we've started integrating ccman2 as well into our package, utilizing periodic integrals now. So the input file for QCPBC looks pretty similar to a typical Q-Chem input file. There's a couple of important differences. So whereas for Q-Chem, when you specify your input system, you give it just a molecule section. We now have a unit cell section, which is very similar to the molecule section. You give the atoms in your unit cell, along with the spin multiplicity. However, we also have this lattice section where you specify your lattice parameters. Then you'll also have a REM section, which is very similar to the Q-Chem REM section. Many of your typical parameters that you might have in a REM section are here again, since we're reusing all of the Q-Chem's SCF libraries and everything. So you might specify your job type and your method. However, there's a few keywords that you're going to probably end up specifying during most of your jobs. For one, we have to specify our auxiliary basis set of plane waves. So this is this KE cut parameter. This is the cutoff of the kinetic energy cutoff of the plane waves we want to include in our auxiliary basis set in EVs. And we'll also have to include the pseudopotential we want to use. So here I'm using a GTH pseudopotential. And then we'll also have to use a basis set that is specially made for use with pseudopotentials. So I'm using this TZVP GTH basis set, which will eliminate all the very compact Gaussian functions that we cannot model with GPW. So for this calculation, I'm running a 3x3x3 Munkhorst pack mesh. So this is a k-points calculation here. You can also run a gamma point calculation, which is just one single k-point of 0, 0, 0, by just omitting this keyword. We also have a few post-SCF methods available currently, so you can specify those with the post-SCF method keyword. So this will run an MP2 job after my PBE0 calculation using the DFT orbitals. And so I just wanted to highlight some of the progress we've made recently now that we have 3 or 4 different people working on it. So as of June 2023, the features we had available were single point jobs for both pure and hybrid DFT, and that was it. We could run both gamma point and K point calculations, but only single points. And so the features we've added just in the last year or so have been we've added MPI implementations to the single points calculations. So I will talk about that later in this talk. I also added orbital Hessian implementations for all the terms we support currently. So you can use those to perform internal stability. We also have smearing now for converting K-point calculations. Q in Junho's group is nearly done with the all-electron implementation, which will allow us to get rid of the pseudopotential dependence in case you want to explicitly model core orbitals. And then I have also added nuclear gradients for all the terms we have for both gamma point and K points. So I will mention that a bit later in this talk as well. And we also, so you can run geometry optimization or force calculations now as well. And we are starting to add post-SCF methods currently. So we have MP2 right now for both gamma point and K points. Shintian helped us port over some of the CCMan2 drivers. So CCSD will be available very soon, at least for gamma points, since I think CCMan2 does not play super well with complex orbitals quite yet. We also have DRPA that's almost done as well for post-SCF. And then just a couple weeks ago, I added TD-DFT for excited states for both pure and hybrid DFT for just gamma point and K points as well. And then we have gamma point EDA done, and I think K points is making good progress as well. So hopefully that'll be available soon. So we've really started adding a whole bunch more features now just in the last year or so as we've started getting more and more developers. But there's, of course, always room for more developers, so we would welcome anyone that wants to add some more features to QCPBC. So the first thing I want to talk about is hybrid DFT. So this is one thing that I think QCPBC does quite well, simply because many other codes struggle with this since it's very hard to do hybrid DFT in periodic systems. And so the main reason for this is that the exchange term, the Fock matrix, couples different K points together. So you can see here you have both a K and a K2. So evaluating this expression ends up being quadratic in your number of K points, whereas pure DFT was linear in your number of K points. So this can get very expensive very quickly. I did just some rough calculations using both PBE and PBE0. So by the time you get up to 9 by 9 by 9 K points, 700 something K points, there's over a factor of 30 difference between pure and hybrid DFT. So for this reason, hybrid DFT is a lot less common for periodic systems. Probably the majority of periodic applications are run using pure DFT still, which is quite a bit different from molecular calculations where probably most people use hybrid DFT all the time just because it's often way more accurate and usually not too much more expensive in most cases. So hybrid DFT is a lot more expensive for periodic systems. So the first big feature that QCPBC added a couple years ago was this awk-RIK algorithm ported to periodic systems. So if you're not familiar with the awk-RIK algorithm, the main idea is that the only important parts of your Fock matrix for an SCF calculation, at least, are the OO block and the OV block. The OO block is used to evaluate energy, where the OV block is used for your orbital gradient during optimization. So the VV block is actually not used during just a normal SCF. And if you have a very large basis set, your number of virtual orbitals can be very large. So the VV block can actually be the majority of the matrix. So by neglecting this VV block, you can actually save a lot of time, especially for large basis sets. So this is the idea of the Akar-IK algorithm. So this is on top of a density fitting approach, which is the RI in Akar-IK. And since we're running GPW, which is already a density fitting approach, it's pretty straightforward to extend this algorithm to solids. So a normal exchange implementation might look like these top equations here, where you have to FFT this sigma nu product from real space into reciprocal space, where you then evaluate the Coulomb kernel from this product density and FFT back. So the number of FFTs you have to evaluate is your n basis function squared times nk squared. So it's quadratic in your basis set size and quadratic in your number of k points. Each FFT additionally costs ng log ng. So your overall scaling would be nk squared and basis function squared ng log ng, which can be very expensive. Whereas if you look at just evaluating k mu I, so you changed one index to occupied here, the number of FFTs you end up having to perform scales only with your number of occupied orbitals. So your overall scaling here would be nk squared, nox squared, ng log ng. So you get a speed up of n basis function squared over n ox squared. And so for very large basis sets, this can be a very large factor. So we wrote a paper on this sort of a couple years ago, which saw speed ups of up to 100 or so, 10 to 100 for many systems using very large basis sets. So this really made hybrid DFT way more doable for much larger systems. It's still quite a bit more expensive than pure DFT simply because of this quadratic nk scaling. But it was tractable at least for small to medium systems. So last fall or so, I added nuclear gradients for all of our terms, including exchange. And so it's worth pointing out that nuclear gradients with GTO-based codes is a little bit more tricky than plane waves because plane waves do not have an explicit dependence in the basis set on your nuclear coordinates. So if you're taking nuclear gradients, you have just the Hellman-Feynman term left over. Whereas for GTOs, you have Poulet terms as well. So evaluating nuclear force with GTO-based codes can often be more expensive than plane wave-based codes. So if we want to remain competitive, we really need to have very efficient implementations of force as well as single points. So with this in mind, I really wanted to get efficient exchange forces. And I think we've accomplished that. Mostly because if you look at the actual nuclear gradients of exchange, it looks very similar to the Akar-IK algorithm. The only difference here is that now you have the derivative of a basis function rather than just the basis function itself. And the bottleneck of the Akar-IK algorithm was the FFTs that we have to perform on the occupied products in the ket here in this integral. So that is totally unchanged versus just a simple Fock build. So hopefully this bottleneck remains the same, then we should expect the exact same computation time for a single point Fock build compared to a nuclear gradient. So I ran some quick timings here for a lead halide perovskite system. So this has 48 atoms per unit cell. Which ends with a TZ basis, ends up giving you almost 2,300 different basis functions in each unit cell. So this is not a trivial calculation. And I did both gamma point and K points. I only did up to 8 K points to save some time. But you can see a couple surprising things actually. First off, the exchange scaling does look, as we expected it to, basically the same between, so I'm showing the single points. This is just a Fock build time compared to a force evaluation. So the exchange time seems constant between the two, both for gamma point and K points, as we expected. So that's a very good sign. So if you can run hybrid DFT to run an SCF, you should also be able to get forces with hopefully no significant extra time. So that's a very good sign. The JXC term has a factor of 3 or 4 in the computation time for K points, which is perhaps what we'd expect from having to contract with gradients rather than a basis function. So that seems in line with what we'd expect. However, the 1 electron terms, which we usually expect to be totally negligible in the overall computation time, seem to scale very poorly between single points and force evaluation. So there's a couple of reasons for this. I think a big one is we spent a lot of time optimizing our 2 electron terms, which we expected to be difficult, and maybe not enough time optimizing our 1 electron terms. However, we're also relying on, at least for the kinetic integrals, on libqints, which I believe does not have some of the more sophisticated integral algorithms, since usually kinetic is just totally negligible. For molecular-based calculations, you really never think about the kinetic evaluation time. So I think if we move over some more sophisticated integral algorithms for kinetic energy, we can definitely speed this up. And pseudopotential is a little tricky since it has kind of a lot of FFTs included in several terms that end up coming out of your nuclear gradient. So we probably just need to spend a little bit more time evaluating that, optimizing that. But overall, our hybrid DFT time looks very good. It does not seem to scale between single points and force for exchange. So now if you can run a single point, you should be able to run a force calculation, which is a good sign. And then kind of the other feature I wanted to highlight that we've added over the last year would be our MPI implementations of single point. So MPI is a parallelization scheme, if you're not aware. It's kind of an alternative or maybe a supplement to OpenMP, which is a separate parallelization scheme. So OpenMP is what most of your Q-Chem calculations are going to use. This is a shared memory parallelism. So you just define parallel regions in code. You just add a pragma OMP4, pragma on parallel, and then multiple threads, which are located on the same physical node, will evaluate that code together. And each thread has access to the memory. So you have to be careful about race conditions there. MPI, on the other hand, is what's known as distributed memory parallelism. So this works by MPI starts multiple processes, which can be on the same node or different nodes. They call these ranks. And each rank will then run the same code. However, each rank has its own memory. So if you want to access the memory on a different process, you're going to have to do explicit send and receive calls to move memory between your different processes. So MPI is a little bit more tricky to code with because you have to think a little bit about your overall structure of the code and how you're going to move the data between your processes. So the motivation here, in part is computation time. So periodic algorithms are what you would call embarrassingly parallel in many cases. For instance, maybe we're just evaluating integrals between different unit cells, which have no dependence on each other, so we can definitely do those in parallel. So you can definitely benefit from into the hundreds of CPU cores for many parts of our PBC algorithms. However, most of the compute nodes that you have on your cluster might have 32 cores or 64 cores. These days, maybe 100 or so maximum. So you're not gonna be able to parallelize super well using only OpenMP. In my experience, OpenMP seems to kind of flatten out after about 16 or 32 processors. You're not getting much of a speed up past there. And in fact, you can't even use more than the number of cores on your CPU. So you're definitely limited using only OpenMP. So by adding MPI, we can actually utilize hundreds of CPU cores, which could give us a pretty large speed up. The other motivation here is memory-based. So I mentioned earlier that we have to store our CGTOs on a grid in real space. So depending on the fineness of your grid, this can be a very large quantity. So the dimension of this quantity would be n basis functions by n grid by number of K points. So your K points is typically in the hundreds. If you're running a very large calculation, you might be using thousands of K points to really get a thermodynamic limit converged result. Your number of basis functions, typically hundreds, maybe thousands for a very large system. And your number of grid points can often be in the millions pretty quickly, or at least hundreds of thousands. So there is some degree of sparsity in this quantity, since for GTOs, these are localized functions, so they're not going to be expanding across the entire grid in many cases. If you have a large unit cell, there can be a large degree of sparsity, especially for very compact basis sets. However, even with sparsity, which we are taking into account in our code, your CGTO objects can be hundreds of gigabytes, sometimes even up to a terabyte or so for very large systems or very large basis sets. So many clusters only offer you maybe 128 or 256 gigs of memory per node. Most computing clusters these days have these big mem nodes, but there's usually a limited number of those. So you really want to only be using maybe 128 or 256 gigs if you can get away with it. So if we can use MPI parallel schemes, then we can utilize multiple nodes, which gives us access to multiple nodes worth of memory. So the other motivation for MPI is memory-based. So the first approach I took to adding MPI parallelism was what I'm calling this grid point parallel MPI scheme. So the idea here is that you split up your grid dimension across different physical nodes utilizing MPI rings. So the benefits here is that you're going to split up this CGTO object. You're going to get a reduction of n MPI, where n MPI is the number of MPI ranks, which would be the number of nodes you're using. Reduction in your storage cost, and the XC implementation, for example, would be very trivial, since each node then can just compute the Fock matrix corresponding to its local set of grid points. At the end of each SCF iteration, you then just add it together all of your Fock matrices from each node. And this would also be applicable to both gamma points and K point calculations, of course. However, it has the downsides that you're going to have to send and receive quite a bit of data. So you'll have to send and receive your Fock matrices at the end of each SCF iteration. For GTOs, our number of basis functions is not super large. So hopefully these Fock matrices are not too large. The communication costs shouldn't be too bad. However, more worrying is that we're going to have to perform these FFTs when we're performing GPW-based evaluation. And FFTs are functions of all grid points. So there's going to be some communication when we're performing these FFTs. So we'll have to use these MPI FFTW implementations. So the communication cost there will scale with the number of grid points, which is quite large. So this could lead to very poor performance for JK in the pseudopotentials, which I'll use FFTs. So I ran some timings here for a benzene molecular crystal. So this has, again, 48 atoms per unit cell, although 24 of these are hydrogens. So this gives you, with a TZ basis set, 750 or so basis functions per unit cell, and something like 375,000 grid points. For these benchmarks, I'm using just 8 K points and 32 threads per node. So over on the right, I'm plotting the speed up versus the number of nodes. So if I so the dashed line in the middle would be the ideal speed up. So if I double the amount of nodes I'm using, I should see a speed up increase of 2. So that's kind of the best speedup that we could hope for in most cases. And then I'm plotting each the time of a single flock build for each of our terms. So the CGTO and the kinetic energy seem to parallelize very well, almost perfectly. So this is unsurprising since each node now only has to evaluate the CGTOs on a small portion of the overall grid. And the kinetic energy integrals, I'm just splitting across the number of, I'm just splitting the lattice sum across the different MPI rings. So that parallelizes super well as well. JXC parallelizes also quite well, not quite perfectly, but you're seeing a speed up of about 6 when you're using 8 different nodes. So not ideal, but still quite well. You're still seeing pretty good benefits up to 8 nodes. Whereas the pseudo potential is definitely leveling off by about 4 nodes. I wouldn't expect to see huge improvements past 8 nodes in this case. And the exchange looks terrible. In fact, when you go to 8 nodes, you're doing even worse than a single node computation. So my takeaway from this is that the MPI FFT calls are very inefficient. They do not parallelize very well, which is perhaps unsurprising due to the amount of communication that they have. So the JXC term has just 2 FFT calls, so it's not a large deal. Whereas the pseudo potential has, I think, on the order of n basis functions, FFT calls much larger. Whereas the ACR-IK number of FFT calls, as we said earlier, was quadratic in the K points and quadratic in your number of occupied orbitals. So it seems that our performance is inversely related to the number of FFTs that we have to do. So it seems like we want to sort of eliminate our MPI FFT calls if we want to improve our performance, especially for a hybrid DFT. So that was the motivation behind this second sort of parallelization scheme that I implemented. So I'm splitting here the K point dimension across the different MPI nodes. So I'm calling this K points parallel MPI. So this is a pretty natural dimension to split across, since you can largely think of the different K points as independent SCF calculations. Of course, they will couple to the exchange and also the J operator. But hopefully significantly less communication is necessary for this scheme. So it's also going to reduce our memory usage, of course, which is nice. And the pseudo potential, as well as the XC implementation, is very easy to do. No communication necessary. Each node just computes the full Fock matrix for a subset of the K points in this case. J will have to do a little bit of communication to get the density. And the ACR-IK implementation will also need quite a bit of communication, however. And the nice thing about this here is that for any quantity that's stored on a node, it has that quantity at all grid points. As you can see, we're no longer splitting across the grid dimension, so we don't have to use the MPI FFT calls. We can just use normal OpenMP FFT calls. Of course, this is only going to be applicable to the K-point calculations. So if you're running a large supercell to model maybe some local defect, then this scheme would not help you in that case. And of course, you can't use more nodes than you have K-points. So if you're running just 2 K-points, you couldn't use 10 nodes, for example. So it requires a large number of K-points to scale up to a large number of nodes. So I wrote out some very brief pseudocode for the J term just to show kind of where this communication is coming from. And basically to compute J, you have to evaluate the density on the real space grid, which will have contributions from all K points. So the scheme here is that each node computes the density from its local set of K points, and then it sends it to all the other nodes. So the communication cost here is on the order of NG times NMPI. So that's a pretty small communication cost. I wouldn't expect that to be a large detriment to our overall compute time. ACR-IK, on the other hand, I won't go too much into the details here, but sort of ends up that you have to, if you're a little bit careful with how you structure the loops, you can end up communicating just a single copy of your occupied orbitals across the MPI. So the size of your occupied orbitals would be NK, NOC, G. So definitely a larger communication cost than J. However, this scales only linearly with the number of K points as well as your number of occupied orbitals, while the whole algorithm scales quadratically with both those quantities. So hopefully it's not a large factor in our compute time. But we can always test that out. So I ran the same benchmark using this different parallelization scheme. So this is again the benzene molecular crystal. And the picture looks quite a bit different now. So you can see our CGTO evaluation scales okay, but definitely not perfectly. Whereas our JXC seems to scale very well. And there's a big win here for our exchange and our pseudopotential. These both parallelize almost perfectly. You're getting a factor of 7 or so speed up when you're using 8 nodes for exchange. So this can greatly speed up your exchange evaluation. The downside here is that your kinetic energy does not parallelize at all, actually. So this is because each node in this case is evaluating the exchange matrix at its local set of K points. However, this is just doing a lattice sum over the exact same integrals. So it ends up that every single node has to recompute the same integrals. So you should probably swap out this scheme for even the grid point parallel scheme where we're splitting up the lattice sum over our different MPI nodes. So that would require a little bit of communication, but would definitely give us way better parallelization for the kinetic term. So this scheme seems to work very well for hybrid DFT, for K-point calculations. So just to kind of highlight the two differences between these schemes, the grid point parallel scheme works for both gamma point and K point calculations and reduces your memory greatly and works good for pure DFT, but not for hybrid DFT. Whereas the K point scheme works only for K point calculations, but gives very good parallelization for both pure and hybrid DFT, while also reducing your memory. So sort of my recommendations would be, if you need MPI, run the K-point scheme if you're running a K-point calculation, otherwise use the grid points scheme. Although both of them should work fairly well for a pure DFT. So those were kind of the two big features that I wanted to highlight that we've added over the last year. Of course, we've added quite a bit more as well. And we are still adding some more features as well. So some of the stuff coming soon that I wanted to highlight would be the all-electron integrals. So hopefully we can get rid of those pesky pseudopotentials and maybe even do some core spectroscopy using QCPBC. EDA should be done very soon as well as a couple cluster calculations should be available. And I would also like to add a sort of freezing string type method so you can optimize transition states for periodic systems. We have all the nuclear gradients now, and we support geometry optimization. However, we don't currently support transition states since we have no sort of freezing string method currently. There's also several features we want to add to speed up our code. So one thing I'm currently working on is space group symmetry. So that should give us pretty large speedups, hopefully for systems with a lot of symmetry. And then hopefully we can also add a multi-grid implementation, which should really help speed up, especially our pure DFT, since I've seen pretty good effectiveness of multi-grid implementations in other codes. So with that, I would like to thank the whole league group for all their help with all the code. I'd definitely like to thank Junho and Shintian especially, who have helped me a lot over the last year or two. And I'd also like to thank Q-Chem.
Perfect. Thank you so much.
Mhm.
Thank you for an amazing talk. It's really exciting to see. I know this has been in the works for several years now, to say the least, and so it's really nice to see all of this come to fruition and see some of the awesome work you've been doing. So I know we've got a lot of questions in the chat, so I'll go ahead and start reading those off for you. And to the participants, there's a little Q&A box down there. If you want to put any questions you have down there, you can go ahead and do so. So the first question is, how does libPBC exploit symmetry beyond a molecular point group level, i.e. throwing away redundant K points? And can phonons and lattice dynamics be obtained with the Hessians that you've implemented? Also, this person says, awesome work, congratulations.
Cool, thanks. Yeah, so the symmetry part is actually what I'm working on currently. So currently we do not utilize symmetry past that, although hopefully in a few months we should support that, throwing away some redundant K points. I just need to figure out how to do that first. So that's what I'm working on currently. So stay tuned, I guess, would be my answer to that. And the phonon lattice dynamics is also what I'm currently working on currently. So we're trying to add the phonon electron phonon coupling currently, which turns out to be pretty complicated, especially for hybrid DFT. But we've got about halfway there, so that should be done as well as later this year.
Okay, awesome. And then we've got this person is asking if this is available in Q-Chem 6.1, which I think I can answer if you don't mind.
Yep, go for it.
So this is not publicly available yet. It is available within the developer version of Q-Chem, but not within the public release version of Q-Chem yet. So we are planning to release it soon. And stay tuned for that. But we yeah, it's not available publicly yet. So, and then they're also asking if they can plot band structure using periodic Q-Chem.
Yeah, sorry, I forgot to mention that. Yeah, we do support band jobs. So there you can run an SCF to get a density at a among-course pack mesh, and then you can also provide explicit path to run a band strap on, and it'll evaluate your bands along that path. So we do support that, yeah.
Awesome. Thank you. And then this person has a follow-up question about the geometry optimization. Is it only for the ground state, or is it also available for the excited state using TDDFT?
Just ground state currently. Yep.
That's figured, but
I added TDDFT about a week ago, so we don't support geometry optimization yet.
So thank you. And then we've got two more questions. So one is, even with the poor scaling with the FFT calls, is GPW still expected to be faster doing density fitting with GTOs or Poisson type orbitals?
Yeah, that's an interesting question that I guess we're kind of working on. So Hugh and Junho's group is working on a density fitting approach with GTOs. So we'll definitely do some benchmarking once that's done. I kind of suspect that GPW will still be faster. I think almost certainly for pure DFT. For exchange, I'm not so sure. I would be very interested to see those timings. So I will let you know.
Nice.
And I have no intuition about Poisson type orbitals. I've never really tried those.
Nice. So thank you. And then the last question, it looks like, is, are there any anticipated issues with PBC runs when performing within non-homogeneous solid vacuum unit cells?
Yeah, I guess we've never really tried any sort of stuff like that. So I can't totally answer.
However, yeah, go ahead. Sorry.
Oh, sorry. Yeah, do you have a?
Well, no. So I was going to say we are looking for fun use cases, and to sort of stress test this a bit before we publicly release it. So that's, if you have any systems in mind in particular, we would love to stress test them
with this?
Yes, yeah, we are. I've actually been running a couple of some various other people's research systems. So I got a catalysis example from Richard and Martin's group. Very helpful. So I've been running that, just a CO2 on a copper surface. And so some of that's, I think we are maybe not super well optimized for that use case. So I think it's definitely worth putting together a suite of benchmark systems to make sure that we're very quick along many different system types.
Yeah.
So if you have a fun example, yeah, it would be worth sending it over.
Yeah. So thank you. All right. It looks like that is all of the questions in the chat. As usual, if anyone has any lingering questions or realizes, you know, a week out that, oh, darn it, I forgot to ask that one. I was really interested. We will have a forum post where you'll be able to ask any sort of lingering questions, and also for folks watching this on YouTube later. Yeah, Sharon, did you want to say something as well?
No, I just wanted to thank Adam for this great talk.
Thank you so much,
Thank
Adam.
you.
And congratulations on
Thanks.
the award recipient this year. We're really excited with all the work you've been doing, and we're excited to see where you'll go next. So, yeah.
Great. Thank you, guys.